Hey there everybody, Mr. D here, and in this video we're going to be talking about graphing rational functions and how to unpack a bunch of values and characteristics from them. So over to the side we have an example of maybe a graph of a rational function, and from what we've talked about so far in this class, we already know rational functions look like anytime we have a polynomial up in a numerator and a denominator. All right, so those are rational functions. Now, graphically speaking, rational functions have asymptotes. And what an asymptote is it's an imaginary line that the graph will approach infinitely but never actually hit. We can have vertical asymptotes that go up and down. We can have horizontal asymptotes that go left and right. Vertical asymptotes, since they are vertical lines, are always written as x equals some number. For this one, we're going through 2 on the x-axis, so this line is x equals 2. A horizontal asymptote goes horizontally across. Since it is a horizontal line, it is always y equals some number, in this case, 3. So vertical asymptotes are always x equals a number. Horizontal asymptotes are always y equals a number. We also have x-intercepts that'll show up, and x-intercepts are really going to help us get the shape of our graphs. Now, an x-intercept is wherever our function hits the x-axis. Well, just by nature of anything touching the x-axis, we'd have a y value of 0. So we're going to write these as -5, 0. Now, we will also have things called removable discontinuities, and that's where, and I'm making this up, if, say, we have a little hole in the graph, meaning a little part of the graph got picked away, so that could be a removable discontinuity. We'll also have y-intercepts, and y-intercepts are where we hit the y-axis. Similar to x-intercepts, a y-intercept will have a 0 showing up. I'm just guessing that that's -7. And it'll have a 0 showing up in place for the x value, because any point that's on the y-axis has 0 as an x value. All right, so now let's go through and get some values based on a rational function. First, we need to come up with a rational function, so I'm going to go ahead and make one up. Let's go x plus 1, x minus 2, all over x plus 1 times x plus 3. Just making that up. So, what we know so far about rational functions is I'm seeing factors that could cancel out, right? These x plus 1 factors, one's in the top, one's in the bottom. If you can cancel anything out, you're going to want to do that because that's what creates a removable discontinuity in the graph, aka a hole in the graph. Okay, so a removable discontinuity is going to happen when any time you have the same factor canceling from both the numerator and the denominator. Whatever this canceled factor is going to help us get the x value for the hole coordinate or the removable discontinuity in the graph. We're then going to take this x value and plug it into the simplified function to find the y value. So here's what that means. I'm noticing that we have the same factors, x plus 1, canceling out. I need to figure out what number for x would result in a 0 for these factors. Well, that value would be -1. Now, the reason why this is called a discontinuity is I'm not allowed to plug in -1 for x, because if I plugged in -1 for x in my original function, I'd get -1 plus 1, that's 0. And if I have 0 in the denominator of a rational, that's technically me trying to divide something by 0, which we obviously cannot do. If you divide by 0, the universe implodes in on itself and everything you've ever known or loved will then cease to exist. So we can't divide by 0, which means we can't possibly have a -1 for x. However, we have a matching factor in the numerator, so those kind of canceled away. So we had this discontinuity point, so this no-no value, but it got canceled out, so it got removed from the function. So that's where that -1 comes from. Now, if I got rid of those x plus 1s, my simplified fraction, or rational, is x minus 2 over x plus 3. So what's written in red and written in blue are technically the same thing. They're going to look the same. The only difference is red has this removed factor still present, and blue is what it looks like after it's been removed. Okay, so we found that x value. What we're going to do now is plug that x value in for x. We're going to plug that in for -1 right there. So up top I'd have -1 minus 2. That's -3. Down below, I'd have -1 plus 3. -1 plus 3 is 2. So I'd have -1 comma -3 halves. Those are the coordinates of the hole in this graph. Again, all we did is just plugged in -1 for x, both top and bottom. So that's going to be an important piece when it comes to graphing. -1, comma -3 halves, that is a removable discontinuity. Now let's go to x-intercepts. X-intercepts are after we simplified. Well, this is what it looks like now after it's simplified. X minus 2 and x plus 3. Oopsies. What would give us a 0 in the numerator? What would give us a 0 in the numerator? So x minus 2 and x plus 3 is our function that we're dealing with now. I'm going to go to each factor in the numerator. Well, fortunately, there's only one. And figure out what number for x minus 2 would give me a 0. That would be a 2. So my x-intercept is going to be written as 2 comma 0. And I'm going to highlight that because that's important, and we'll come back to that when it comes time to graph. So far on the graph, I've kind of found two coordinates, if you will. I've got a hole in the graph, and I've got an x-intercept. A vertical asymptote is what is created after we've simplified out our original rational. It's what would give us a 0 in the denominator. Because remember, we can never divide by a 0, so I need to make sure whatever number I plug in for x here doesn't result in a 0 for this factor. So I need to figure out what is an off-limits value for x. Well, that would be -3, because if I plugged in -3 for x, -3 plus 3 is 0. Can't have that. So I'm going to have a vertical asymptote at x equals -3. Again, I'm going to highlight that just for safekeeping. And now let's get into our horizontal asymptotes. Horizontal asymptotes kind of have a bizarre rule. Now, arguably, it has the least amount of thinking involved. However, it is the most easily forgotten one. Now, horizontal asymptotes will give you one of two things. It's either going to be y equals 0, or it's going to be the ratio of the coefficients. So let's focus on scenario 1. When will our horizontal asymptote be y equals 0? This is going to happen if the degree, or the highest exponent from your numerator, is less than the degree or highest exponent of your denominator. So here I have an x squared over x to the third. Or here I have 2 factors with x over 3 factors of x. So this is technically an x squared. This would be an x to the third. Here I have an x over x squared. Anytime the power of the x's up top is less than that in the bottom, it's automatically going to default to y equals 0. Now, if it's a tie, meaning you have the same x power up top as you do down below, so my exponents here are 3 and 3, so cubed and cubed. I've got 1, 2, 3, and 1, 2, 3 x's being multiplied there. I've got a squared and a squared. Well, then it's going to be the ratio of the leading coefficients. And the leading coefficients are the numbers attached to that highest degree term. So I'm kind of boxing these up here. So for that first example, I have a 4 over 1, so the horizontal asymptote would be y equals 4. For the second one, there's technically a 1 chilling out front. I'd have y equals 1/2 is my horizontal asymptote. For that last one, I'd have y equals 3/4 as my horizontal asymptote. So in this class, we're either going to see y equals 0 or y equals some constant number, and that's all going to depend on the degree of the numerator as it compares to the degree of denominator. Now, later down the road in future classes, you will see scenarios in which the degree of the numerator is bigger than that of the denominator. And that turns into something called a slant asymptote or an oblique asymptote, which are also referred to as end behavior lines. Now, for this particular function that we've been dealing with, I could either do the original function that we had in red prior to simplifying things, or I could use this function that we simplified over here in black ink. I'm noticing there's an x to the first up top, x to the first in the bottom. So it's a tie for the x power, if you will, which means our horizontal asymptote for this example we're dealing with is going to be y equals 1, because we had a 1 over 1. All right, so I've found my removable discontinuity, I've found my x-intercept, I've found my vertical asymptote, I've found the horizontal asymptote. All that's left is finding the y-intercepts. Well, to find a y-intercept, all you got to do is plug in 0 for x, simplify, and see what you get. That doesn't sound too hard. So let me take my function. We're going to plug in 0 for x and see what y pops out of it. So 0 minus 2 all over 0 plus 3, negative 2/3. So my y-intercept is 0 comma, 0 comma, negative 2/3. All right, hard stuff is done. The hard stuff is done. Now it is time to graph. I'm going to go ahead and steal one of these graphs from this graphic section here. And let's compile what we have. All right, I've got a removable discontinuity. So I'm going to be kind of stealing and copy pasting a bunch of stuff down below. Got a removable discontinuity. I've got an x-intercept. I've got a vertical asymptote. I've got a horizontal asymptote. And then we just found the y-intercept. So I'm going to take all of this and kind of compile it as framework. All right, so first point, we have a removable discontinuity at -1 comma -3 halves. -1, -3 halves, that's really like a -1.5. That's going to be right about here. So -1 comma -3 halves. We'd have a hole in the graph, so just a hollow circle right there. All right, next we have an x-intercept. An x-intercept at 2. Well, I'm going to go to the x-axis and just put a dot on the 2. So we have an x-intercept at 2. Next we have a vertical asymptote at x equals -3. So I'm going to go to -3 on the x-axis, and I'm going to sketch in a vertical line. So this is the line that my graph will never cross. This is kind of like an imaginary dotted line. It's not part of the function itself, but it does help to have it graphed just for our frame. Let's see if I can get a better color here. Okay. We have a horizontal asymptote at y equals 1. So a horizontal asymptote across the y-axis at 1. Now with horizontal asymptotes, we are allowed to cross it, but as we go out forever to the right or out forever to the left, we are going to mirror and approach the behavior of that line. All right, and the only thing that's left is our y-intercept, which was 0 and -2/3. 0 and -2/3. So that would be roughly right there. All right, so now we have the framework. The hard part is over. Now, when we graph this, we need to keep two things in mind. One is I will never have graph above graph, meaning a function will never be graphed directly above or below itself. Clearly, I'm seeing there's some points and things happening down here. So part of my graph is going to have to exist down in this section. I'm going to go ahead and sketch that in. So we're going to exist down in this little section here. I'm going to skip over that removable discontinuity, because remember, that was one single point that kind of got plucked away. And then I need to figure out, well, what's going on over here? I can't put any sort of graph up top here because I'd have graph above graph, and that's no longer a function, so I can't have that. I cannot have graph above graph. So I might have a little bit of graph down here or a little bit of graph down here. But I don't really have any points to go off of. Well, here's where I can use a little logic. I know that I can't possibly have a graph down in this section, because if I did, I know I need to approach this asymptote and I need to approach this asymptote. At some point, I would need to cross over the x-axis. And if I crossed over the x-axis, I would have an x-intercept. And if there's an x-intercept involved, we would have known about it. So since there is no x-intercept, it can't possibly exist down here, which means the other portion of my graph must be up here. So it's going to approach both asymptotes. We don't have to be perfect with it. And that would be our function. So by finding all of those features of the graph, what we've done is kind of provided a framework and a little guide for ourselves to graph that function. All right, folks, that is it. That is all for this portion of the video. In the next video, we will go through and graph these functions provided. You know the drill. If you have any questions, do not hesitate to ask. And as always, folks, good luck, have fun, be safe, roll tide.